Hello everyone. So this is the class CBC class 3 and the continuing that the same correlation and regression class. And here especially we are going to concentrate on linear regression. Now you can see that here what is the linear regression first before going to the topic we need to know about that what's the linear regression, because in last previous class we understood that the correlation and so what's the importance and what are the problems are there, what are the methods are there, what's the um, limitations are there, advantages, so etc. And everything you have gone through that, right? So you hope you understood, and I had given that in offline class also a little bit about that the correlation and regression also I explained. Adding on to that here, the using that here a little bit more adding to that the those points, right? Now a linear regression is a data plot that graphs a linear relation between an independent and a dependent variables, right? So, and which is typically used to usually how the strength of the relationship and the dispersion of the results. Come to that here with examples to see the test the strength and relation between amount of an ice cream eaten and the obesity. So it's related to that how much the I mean strength of those two variables, right? And take the independent variables, the amount of ice cream, and related to the dependent variable obesity to see if there was relationship. And in correlation, have you observed that both will be the dependent, I mean independent variables. Now here independent variable as well as the dependent variable. And next, mathematical formula is here y equals b naught plus b1x plus e also. The same thing I think I explained y is equals to a plus bx also, which is a linear regression, a line equation, right? And here single variable we used. How you know what this is the b1 into x. So this is the input we need to take that. And e is nothing but the error mark. And these two are the coefficients, right? So this we are going to predicting that thing, right? Now, multivariables will be there. So we can't predict that always in a single variable, no? So then b naught plus b1x and so on, and bp and then xp plus dash 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 plus finally we are taking that the error like that. And what we use a linear regression for this, right? The overall idea of linear regression is to estimate two things, right? So does it set off a predict variables to do a good job in predicting outcomes of the dependent variables? And then second, which variables are particular or significant predictors of the outcome variable? In that way we can indicate it by the magnitude and sign of the beta estimates impact to the outcome variable. Now, key points when we're selecting that the model of the analysis, and an important consideration is a model fitting here. So that's what you are saying, that how the regression line is going to fit. Adding the independent variables to linear regression model will always increase and explain variance of the model. Typically, we can express that R square. You can observe that there also coefficient of correlation with R square also we have gone through that, because when we are taking into the test of hypothesis. Similarly here also, overfitting can occur by adding too many variables to the model, which reduces that the model generalizability, right? A simple model is usually preferable to more complex model also. And statistically, if a model indicates a large number of variables, a sum of variables will be statistically significant due to chance alone. Now come to that by taking that example here, simple linear regression. We have taken that one college bookstore must order books 2 months before each semester starts from the library data. They believe that the number of books that they will be sold for particular course is related to the number of students registered for the course when the books are ordered. They would be going to develop a linear regression equation to help a plan how many books to order, right? From past records, the bookstores obtain the number of students registered and the number of books actually sold for our course. So 12 different semesters we have taken, a number of students, and then this is the data related to the number of books also. Now here another term also is we are going to add, because already when we are seeing that the formula also we have seen that plus adding that e also. In a statistical or mathematical law which is created when the model does not fully represent actual relationship between the independent variables and the dependent variables. There are term is also as the residual or disturbances or the remainder the term. Now Within a linear regression model, tracking in a stock's price over a time, the error term is the difference between the expected price to particular time and the price that was actually observed. And the next, the instance where the price is exactly that was anticipated at a particular time, the price will fall on the trend line, and it becomes to that the error term becomes to 0. So those 2 points, we can see that the error term stands for any influence being expected to on the price variable, such as changes in the market sentiment. Now you can see that here also, when you are taking these all the things, all are going to fit, depends on the variables. If one variable will be there, this you are going to use. If two variables are many, multiple variables are there, we are going to fit like this. So then we can see that the how much the term is the curve is fitted based on the data sets, right? So that we can see that here. Now simply I kept that here, this slide, for how you are going to make that the error calculation. So the residual calculation is R I. In general, we can represent it with a yi minus y bar, and residual value and observed value and predicted value, um, by taking y is equals to next plus 2. The residual of each observation can be found by using like this data. So this is very simple because I can't take that 1 to 12 the library data. So x values are y values, and we can calculate that y bar, that means these thing, and error also we can calculate by using this residual equation and then square of that, right? And we'll get that like this. Residual standard deviation is nothing but 1.414, right? So loss function also we can see that in class I told you for SVD and all, no, in offline classes, the loss function also we can take the more very important, minimizing that data, minimize all these. So one of the class function we can see that here. Every machine learning problem is basically an optimized problem. That's what I say, that when you are learning that ML, so these functions will come, right? So this one of the function we are going to see that here. The function that you want to optimize is usually called as a loss function or cost function. Both will be the same. For the house price prediction example, after the model is trained, we are able to predict a new house prices based on their features, right? So here also we can see that for each house price, we can predict that which is represented with yi, and actual house price is yi, and we can calculate that loss by loss function yi minus y bar, sorry, yi bar minus yi whole square. This is the loss function formula, and we can use that using here in a quadratic loss or least squares also we are going to use, and which minimize the loss function maximum it is possible to prediction will be the close to the possible to the ground truth. And the graph will be like this: obtain a scatter plot of a number of books sold versus the number of registered students. This the first I showed you, know, I mean this right, this data I have taken already again. So it comes to like this, okay, because the data is available in our college, so we kept it like this. And comparing model predictions against the reality, right? Response equals to constant plus predictors plus error. Response and output is estimated by the given any given input or set of inputs. Check these estimates against the actual values to that the residual values. And residual, see, we can see that these residual, and if the residuals are small, then the model is very good estimator. That means error is small, right? And mean behavior error also the same thing, and we can go with that this the formula will be like this: mean absolute error. We can calculate the residual of each day every data, because 12 data sets, so you have taken, no, 12 semesters, right? So data taking only the absolute value of each, and so that we can get that negative or positive residuals, do not cancel out that, right? So take the average of all the residuals and we'll get that the mean. That's nothing will be there, right? So this is the graph, we can see that here. So these are all the math. So here each residual contributes a proportionality to that total amount of the error, and meaning the large errors will be contribute like linear to that overall error. And here very small model is a great prediction that once the MAE is very small, then we can get that very good prediction also. And if MAE, suppose we are thinking that MAE is absolute error is 0, the model is perfect predictor of the outputs. But this will be almost never happen, because anywhere will be there. That's what you are saying, that in desktop hypothesis 5% error, 1% error, and 10% errors, right? Same. And this is one more mean square error, squaring of that. Previously, you can see that here we are not squaring here, mean absolute error. But when come to that mean square error, we are making into that square, right? Both the values, and the value will get like this. Next, come to that mean square error. The effect of the square term in MSU equation is most apparent with the presence of the outlier in our data. Each residual in MAE contributes proportionally to the error. Error grows quadratically in MSE. Outliers in our data will contribute to too much total error in MSE. They can be MAE. And come to that here now, root mean squared error, RMSE. So here RMSE is analogous to the standard deviation, and MSE to that variance is measured to how large your residuals are spread out, right? So now you can see that the first onwards, first MSE, MSE A and B, and then next RMSE A, and then RMSE B. Like that we can see that root mean squares. And mean absolute percentage error also will be there. Now we observed 1 by n, and then summation of that and squaring of that. Now the percentage also we are going to see that. So when you are taking the percentage, see where it is going to get that the percentage of these, right? Previously we observed here and there, this, right? Now you can see that the percentage of this, right? So here you'll get that the graph will be like this. And finally, so this is the percentage error continuing the same here. N equals to 1, y 10, and y equals to 20, y bar 10. Now you got that MAP is 50%. If you increased, that means getting into that y bar is 20, and y is 10, and now you are getting that 100%, right? I can see that here the data, right? If error will be the less, and you are getting that the full of the outcome. So like that, now the percentage same, continuing the same, lakhs. Finally, unlike MAE and MAPE, MPE is also useful. It allows to see you our model is systematically underestimates more negative error or the positive error. And residual plot, in correlation you observe that scatter plot like that. So here residual plots also. After you fit a regression model, it is crucial to check that residual plots also. So if the plots displays unwanted patterns, you can't trust the regression coefficients and other numerical results also, right? So residual plots displays that residual values on the y-axis and fitted values or another variables on the x-axis. So essential parts of the especially regression model will be dependent variable, and this dependent variable is constant plus independent variable plus error, right? So I said that like that. Dependent variable also deterministic and stochastic also. If it is a stochastic, what? So unpredictable. Yes, we know that we have seen that unit 5 stochastic process also, right? Better to understand that they come getting into that the knowledge of unit 5. The differences between the expected value and the observed value, and series of errors also should take look into that the random. That's what we solve the problems, like taking that long run you have to solve the problems, and taking into that the TPM transition probability matrix by ergodic model or regular model. That's all those things you can suppose if it is a deterministic. Then what? So if it is a deterministic component, is the portion of the variation in the dependent variable that the independent variables explains. All of the explanatory powers should reside here. Like R squared is a goodness of fit measures of a linear regression model. So don't think that here the regression goodness of fit is not the same as what you studied in a COSM, right? So there the goodness of fit is one of the model in a chi-square test, right? So here in a regression model also we are going to see that is a goodness of a fit measure for a linear regression models. It indicates the percentage of the variance in the dependent variable that the dependent variable explains collectively. R squared indicates the relation between your model and independent variable and convenient to 0 to 100% scale. The R square is always going to that between infinite and then 1. Small R squared values are not always a problem. High R squared problems are not necessarily good, right? So the last line is very, very important. R squared interpretation also like this. You can refer the Python code also. This is the example you had to do that, girls. Linear regression, whether it is fitted or not. And this you can take it out. Otherwise, previous also we can take it out. Interpret p values and coefficients values also. So I explain p values and all and t test also. If you are not getting, and again ask me, I can explain you. So this is the course beyond syllabus, no? Right. The same. I think you know very well, no? From the basic starting the test of statistics, regression analysis is also one of the form of inferential statistics, right? And this is the summary, girls, right? Sarconia is like this: mean absolute error, residual operation is the absolute error, and goes to the outliers is S. Key observations: what magnitude of the residuals or larger errors will contribute linearly to the overall error. And then small MA suggests that the model is a great at prediction. And key observation does not, this model, Nana, does not indicate if the model under or overshoots of the actual data. And a large MEA suggests that your model may have a trouble in certain areas. And come to that MSE, residual operation is squared, outliers is low, key observations are analogous to the variance, error grows quadratically, and overestimating of the badness, this we can see that, right? And RMSE, root mean squared error. Now we can see that here everything affected by the outliers. And MAPE, Nana, and design of data points where that value is 0 can grow unexpectedly large if actual values exceptionally small themselves, and then biased towards predicts that are systematically less than the actual value. Finally, MPEs. Last one you can see that since positive and negative errors will cancel out, I cannot make any statements about how well the more model predictions perform overall. That's the thing. Parameters, this you can see, because when you are coding that one, that we can see once. Important is that here there must be a linear relation between independent and dependent variable. Multiple regression suffers from multiple linearity, autocorrelation, heteroscedasticity. Linear regression is very sensitive to the outliers. It can be terribly affect that the regression line and eventually the forecasted values. Multicollinearity can increase the variance of the coefficient estimates and make the estimates very sensitive to minor changes in the model. The result is that the coefficient estimates are unstable. In case of multi-independent variables, go with the forward selection or backward elimination stepwise for selection of the most significant independent variables. Right? So these are all the linear regression graphs. You can see that here different thing. Assumptions also. It related to the girls. Python code. You can see that pandas and all. Right? Okay. So this is also why why we are, how should we use the linear regressions. Okay. And use cases also. Previously we know that many are there here. see astronomical data analysis also we can predict by using the, we can fit the data, Nana. Studying engine performance from test data into autonomous automobile. And the graph will be like this mark. Okay, hey, you can see that the same graph when we are plotting in a Desmos app, no, so the same thing, geometrical institution, right? We are like this. Okay, so if we are putting that here, this 10, now see how the graph will be like this. Okay, now you can see the different parallel things, the graphs. Okay, so I need to, can I ask these questions like linear regression is a supervised machine learning algorithm, is it is true or false? And so these are all the questions. You can check it out that after, and you have to I mean put that submit the poll, or when I'm conducting that the 1 minute thing, right? You can respond like this, and here also which method can fit the data for the linear regression, all those things. I'm sending that this PPT also. Keep it with you and go with that. Okay. So these are all the questions. Without fail, you have to do the else, right? So I have given that few of the things answers also, but you can. Thank you so much, girls, for attending that third class. Thank you. See, if you're not getting any doubts, you can mail me, you can text me in WhatsApp. You can ask that, and after the class also. Okay. So hope that you understood that is this course beyond the syllabus. Third day of the class. Right? Thank you. Thank you so much, girls.